So here's some examples of looking at linear diophantine equations. At this point, we don't have a lot of fancy tools. We're not using the fancy tools we already have, actually, but just looking at the basics of linear diophantine equations. So let's look at an example. 12x plus 19y equals 1. And one of the things that the book does is suppose somebody has given you a solution to this equation. How can you build upon that? And in the next section, this is section 4.1, by the way, of the book, in 4.2, sorry, 5.1. In 5.2, we're going to see that the Euclidean algorithm actually is really already an algorithm for finding a solution. But suppose we just have this, okay? We could check it, okay? What does that mean? It means that 12 times 8 plus 19 times minus 5. Okay, that's 96 minus 95. Yeah, that's 1. Okay, doesn't mean anything weird or new. Okay, we can also check it graphically. It's nice to think about this idea of that's a straight line, and we're just saying, does it go through what's called a lattice point, or just one of the grid lines in integer space graph paper? Let me just bring this up a little bit. There we go. Okay, and indeed, if you notice, if you look at this line, I just graphed the equation, it doesn't go through most of the grid lines intersections, but right here at 8 comma minus 5 it does. So that's a graphical picture of saying this is a solution. Okay, so what can we do with that? Well, one really important but simple thing is that we can solve associated equations really quickly. Okay, if we know that 12 times 8 plus 19 times minus 5 equals 1, well, how would we get a solution to 12x plus 19y equals 5? We just have to multiply our solution by 5. So 5 times 8 plus 19 times 5 times minus 5 is going to be 5. So in other words, xy 40 comma minus 25 is totally going to work. Okay, so one reason that's important is it says we're going to specialize to solving the case where the right hand side is 1, and we know that there's a very simple way to relate that to when the right hand side is not 1. So that's one reason why that tends to be a specialization a lot of the time. So for example, really similar case, if we want to solve this new equation, notice that's a negative number on the right hand side. Not special, really fine. 12 times, I take out my solution I already know, and I multiply by minus 3. 19 times minus 5 times minus 3. That's going to be minus 3. So that's a pretty simple procedure. Okay, so now a little bit harder, not too much harder, but a little bit harder is, let's go back to the original equation. So now we can say, oh, okay, we really want to concentrate on these equations where the right-hand side equals 1 most of the time. What about another solution to that equation? It's probably not true that this line only ever goes through this lattice point. There's probably more solutions than just this to that equation. So we could start trying to think, what can we add to x to not screw this up? Okay, well, we could try adding 1 to x. Okay. We try adding 1 to x. Then that's going to increase this by 12. Can I simultaneously decrease this by 12? Not really. Because this guy's got to be a multiple of 19. Okay, well, what if I increase this by 24? Like increase x by 2, that increases the 12x by 24. Can I cancel that out by decreasing this by 24? Not really, because this has still got to be a multiple of 19. Okay, and what's the crucial thing about the 12 and the 19? Well, that was what was required to actually have this have a solution in the first place. Okay, we know that the GCD of x and y is 1. This is one of the things they talk about in this section, but it's fairly clear. If they had a common factor, there's no way that this would have that same common factor, and if that's not just 1, then this couldn't be equal to 1. Okay, so to have the solution at all, we know GCD of xy is equal to 1. Okay, so that means if I ratchet this up, it's going to ratchet up by multiples of 12. This guy, to compensate, has to ratchet down, but it ratchets down by multiples of 19. And there's no common factor there. So what we discover is that we must, yes, we can do this, we must increase x by a multiple of 19 and decrease y by a multiple of 19. And this is going to be in section, oh, what was it? What is it, 4.3? No, sorry, I'm getting it totally wrong. 5.4. Okay. This is really already going ahead to 5.4. That's the only way we cannot screw this up. Okay, so for example, we could just take 12 times, let's see, what was our basic solution? 8, and then I'm going to add 19 to it, plus 19, take my basic solution, and subtract 12 from it. Well, I've now added 12 times 19 to one of the terms and subtracted exactly the same number, but expressed in a slightly different way, 19 times 12 to the other one. That's still going to be equal to 1. And I have that drawn out in the picture. You have to go a little further on the graph. On the graph, what we see is that here's that solution, 8 comma minus 5, right? I can't really click on it here. And then down here, here's 27, 8 plus 19, comma minus 17. It refuses to give me a grid point there at the odds, but it's okay. But that's 27 comma minus 17. And that's exactly the solution here, 27 for x and minus 17 for y. So, and then we can just keep going. We can keep marching by multiples of 19 here, multiples of 12 here. So that really kind of gives a lot away from even later sections. Okay, so now, finish up this video. I don't want to make it too long. What about this equation? All I did was I changed the 18 to 19 to an 18. Very minor change, seemingly. Is this going to have solutions? Okay, well, that gets at something I was just saying. Notice that 12 and 18, very different pair of integers from 12 and 19. 12 and 18 have a common factor. Okay, so since the GCD of 1218 is 6, that's not equal to 1. The left-hand side is a multiple of 6. It's just the linear combination lemma. Okay, I'll capitalize that. Now it's the start of a sentence. Okay, so this is impossible. No solution. Okay, that's lemma. Oh gosh, what is that called? What do they call that? That's the very first thing they proved. Okay, in this chapter, that you can't solve this equation when the GCD of this is not equal to 1, when they're not relatively prime. Okay, now this one's a little trickier. I'm not trying to set it equal to 1 anymore. I'm going back to these ones where there's not a 1 on the right hand side. Now we know that fundamentally we can really concentrate on ones with the 1 on the right hand side. But just to get our understanding better, we can look at something where it's not 1. Okay, well, but still the same thing applies. Okay, here the left hand side is still a multiple of 6, but 3 is not a multiple of 6. Okay. So now finally this one, okay, this one may well have a solution. Okay, and you could attack that directly, but the way the book would suggest to do it, and a really good way to do that, is let's get it back to this case where it's all about relatively prime. It's really pretty. It's all about the Euclidean algorithm does really well with that. We'll see. Let's just go ahead and divide everything by 6 if it has a common factor. So exactly what you do just to simplify things in general, divide out by that common factor. It's exactly the same equation as, 2x plus 3y equals 1. And then forget this ever existed pretty much, because it really has the same information content. So that's previewing a lot of the stuff from chapter 5.